Okay, we start. It is a pleasure to introduce Professor Thomas Mountford, who will speak on invariance principle for Markov Cookie random walks.
Thank you very much. Thank you very much. Sorry. It's a great honor to be here, and I come to South America quite a lot, so I feel I'm among friends. The talk is going to be not really a high-tech talk. It'll be but there will be things that it's about Markov cookies. So it's a little bit of a niche subject. So nothing will be particularly hard, but there will be things that I think I need to prepare the ground. So everything should be, feel free to ask questions if something isn't clear, because everything is, as I said, not high tech. So if something isn't clear to you, then, well, it's not you, it's me, okay? Okay, so this is joint work with Kosygina of Baruch and John Peterson of Purdue. So, as I say, it's going to be mostly a sort of micro mini course in the sense that I'll be talking about cookie walks, which not everybody will know about, and then I'll be talking in the second part. Excellent. Okay. Then I'll be talking about the main intellectual ingredients of the talk, which are a paper and an approach of Bessel and Singh, and the ideas and results of Balint-Tot, and then just talking about how we apply these ideas to get our result, which is really just a common and garden diffusion approximation. Okay. Okay, so a cookie random walk is a non-Markov process. I'm going to be talking just about cookie random walks on Z. It's important because it'll just, I can only use my Ray-Knight approach, the approach of Bessel and Singh, there. So the idea, though, is that typically you have a sequence of values for every point in Z. You have a sequence of values omega z, which is a sequence of values, probabilities. And so omega x1 is simply the probability at the first visit to x that afterwards you move to your right. And therefore, the probability you move to your left is 1 minus this probability. Okay? We want this pile of cookies to be independent as from the sites, and independent with the same distribution. We've assumed basically we're being a bit lazy, but we assume the probabilities are always bounded away from 0 and 1. And we'll get to this in a moment. And so the idea, why it's called a cookie random walk, is just that each of these values are cookies. You have a pile of cookies. Every time you move, you eat a cookie, remove it totally, and then you move according to the value of that cookie. Okay, it's also called, which I like, Brownian motion, but that didn't catch on. So a bit of history. These were introduced by Benjamini and Wilson. They weren't called cookie walks, they were called excited random walks, or in their case, once excited random walks. And there we had just the basic model, which was there is one cookie at each site, and so that there's a probability between, and they chose a probability between 0.5 and 1 of moving in a certain direction, because they weren't just on Z, they were on ZD. And there, the real questions that people addressed were, if you're in 2 dimensions or 3 dimensions, is the cookie random walk, if you're biased, let's say, in the X direction, is the cookie random walk transient or recurrent? And I think, in, let's say, 2 dimensions even, you can say, sure, it's got to be transient because you keep getting pushed. But it's not so easy to prove it. It's really, the arguments given by Benjamini and Wilson and then Gabby Cosma were very hard and complicated. And then it was really, I think, to me, nailed down by Ramirez and Berra, and then Ramirez, Popov, Vashkovskaya, Menshkov, who gave a very wonderful proof of transience under very general conditions. But from now on, everything is going to be in one dimension. Okay? So, a key point here was, the key result was from Badevin and Singh after much work. And there they look, for each pile, you have a pile of cookies, and we choose it so that this sum, infinite sum, is well defined. Typically, we were thinking about a finite number of cookies. You have a finite cookie stack. And you have delta, it's just the drift. It's a totally natural thing to look at. And so Badevin and Singh just worked out that if you will go to the right, if and only if this drift is greater than 1, and if it's greater than 2, you will actually go ballistically quickly. Okay? So, in fact, they didn't use these full conditions. They just considered P was between 0.5 and 1, and there were only M cookies, but they could have done it. They were just, that was in there as far as they were concerned, what a cookie random walk was. Okay? So we will be talking about Markov Cookie random walks, which was introduced by my two co-authors. And here it's different because, unlike Badevin and Singh, the cookies don't go away. What we have is at each site on Z, you have a Markov chain. A Markov chain on a finite state space, irreducible, nice, it's a very nice basic thing. Just think of maybe 2 values if you like. And then you have a function from the values of the Markov chain 2, 2, 0, 1, giving you probabilities. Okay? It's a slight increase in generality because the cookies aren't the values, because it could be you have 2 different values which give you the same probability, but the future behavior will be a bit different. But anyway, so the cookies never go away. We have, as I say, the probability of moving to the right when you're at xn depends on the cookie on the cookie or the Markov chain value for the Markov chain at that site, evaluated on L, the local time, the number of visits to X at that time. So you can also think of it as the Markov chains only evolve if they're visited, if you like. But either way, it doesn't matter. The Markov chains all have the same distribution, the same laws of evolution, but they are they evolve independently, and we suppose, for simplicity, that they start off also, the initial first value of the cookie is IID. So you can think of this, well, let me just say, you have a Markov chain. If you forget about the cookies for now, you just have a Markov chain. That gives you a probability, a stationary probability. Everything's irreducible. You have a stationary probability. If you look at the stationary probability, you can integrate the function P with respect to the stationary probability, and that gives you a number between 0 and 1. If this number is not a half, it's very easy to see, and you can, no need to go into the proof, but you are pushed along. There's just, the law of large numbers is so large, you can't fight it. You will, if the integral of P with respect to the stationary distribution is greater than a half, you'll be pushed to the right, and there's nothing to say. Okay, so from now on, I will be assuming that the integral of the function P with respect to the measure pi, the stationary measure pi, is going to be a half, okay? So actually we'll see that the Badivan and Singh approach can be generalized to this. This was done by my two co-workers, and you can get, in this situation, good, necessary, and sufficient clean conditions for transience and recurrence, okay? I'm going to talk about when you have recurrence, but not the critical cases. So there are two parameters, delta, delta dashed, and you have recurrence if both of these parameters are less than or equal to 1. I'm going to take them to be strictly less than 1. If one of them is 1, you shouldn't expect the nice limiting behavior. It's just not going to happen. The critical case is too weird, okay? But if it's a nice recurrent process, we should, of course, expect Brownian behavior when you renormalize, okay? You should expect Brownian behavior, but my next slide is to say, what does Brownian behavior mean? What is Brownian behavior in this context? So in this context, we're looking at what is called Brownian motion perturbed at extrema. So this is defined if alpha is less than 1, beta is less than 1, and it's not obvious, but it's the unique pathwise solution to this equation here. So the idea is, when you get to the maximum, you also get a bit of a push, just like a reflecting Brownian motion. When you get to 0, you get a push. It's the same idea, okay? You get a push. There's no problem with alpha or beta being minus 1,000,000. That's fine. If alpha is minus 1,000,000, then what happens is when you get to the maximum, it's like going against a wall. You just bounce off it and you're pushed way back, but the wall has moved a little bit. Okay, that's sort of what's happening. On the other hand, if alpha were greater than 1, if your Brownian motion is at the maximum and it moves by 1, well then the maximum is going to go up by 1, but then your process is going to go up by alpha, 1 plus alpha. But then going up by 1 plus alpha, it's going to go up by another 1 plus alpha times alpha, and so on, and so on, and so on. And I think it's pretty easy to see you really do need alpha to be less than 1. Otherwise, your process is just going to shoot off to infinity. Okay? Anyway, as I say, there's a big list of illustrious people there who've worked on this. So I think it's time to give our result, which is, there are two parameters. I haven't told you what they are. I will do. Delta and delta dash, tilde, which if they're both less than or equal to 1, we have recurrence. I'm going to take away the critical cases, so it's just going to be minus 1 to 1. And then we have this process, our process suitably rescaled according to diffusion, diffusively rescaled, is going to converge to square root of 2 over sigma squared times this Brownian motion perturbed at extrema, where I haven't told you what sigma squared is either, but that will happen. Okay. So this follows from and this is in some sense expected, or the natural thing to look at, from preceding work by Dolp-Goyat and Kosygina. You have this result for the cookies in the classical case. The classical cookies, you have m finite number of cookies, then provided the delta, which we've already defined, I've said that's between, yes, you want it to be between minus 1 and 1, that is correct. Then this process, suitably rescaled, converges to Brownian motion perturbed at extrema. Notice there is no sigma in here, but that's to be expected because when you've used up the cookies, you're moving like a Brownian, a simple random walk, and that's going to give you Brownian motion with no sigma. Okay, the proof is quite reasonable, really. What you have to say is, if you look at your x, your cookie random walk, depending upon the cookie, it's going to move 1 or -1. So you apply the compensator. You know what the compensator is. You take away, you compensate it, you have a martingale, and now you say to yourself, you can prove your cookie Markov chain is going to be, it's going to eat up all of the cookies at the sites it visited, more or less. Of course, there's going to be a couple of exceptions, but basically you're going to eat up most of the cookies that you're going to, most of the sites you visit will have no cookies. So your martingale, if you look at the variant or the bracket process, whatever you want to call it, your martingale will converge to Brownian motion when you've renormalized it. On the other hand, the push is going to be, well, you look at where you are, more or less if you're -1 square root of n is the minimum, 2 square root of n is the maximum, you will, broadly speaking, have eaten all of the cookies in this interval of length 3 square root of n. So you will have had a push of 3 square root of n, which is basically a push of, when you renormalize it, the maximum minus the minimum. That's the range, okay? And that's why it's delta and minus delta, okay? So this is perfectly reasonable, logical, and I dare say expected. Okay. So now, another result this was proven, but in the case where the Markov chain is periodic, cyclic, trivial. You move deterministically from 1 to 2 to 3 to up to n, and where I've ordered the cookies. Okay? So, in this case, we have this formula, sorry, theta and theta dash, sorry, that's, I lifted it, that should be delta and delta tilde. It's the same thing, okay? So in this case, it was proven, the result we wanted to show was proven, and the difference is that if you have this periodic case, remember the integral of p with respect to the stationary measure, which in this case is just uniform on these cookies, these m cookies, the integral is a half. So if you look at the drift resulting from a single site, that's a bounded quantity. As you do one cycle, the drift is 0. So that's bounded, and that's enormously helpful. We can't really do this. But on the other hand, you might say to yourself, okay, but we should expect this result just by analogy with the first result where you have a finite number of cookies. You can say to yourself, we start off with our Markov chains in some distribution, an arbitrary distribution. Okay, in an arbitrary distribution. This is going to provide, it won't be in an equilibrium, it's going to provide a push. But equally, your Markov chain is going to get to equilibrium very, very rapidly. When it gets to equilibrium, it's going to be fair, equal, okay? Because under equilibrium, you're as equally likely to go left and right, okay? So the initial distribution is like the pile of cookies. The stationary distribution, you might think, is like no cookies at all, and you move left and right with equal probabilities, okay? As it turns out, that's sort of right. I mean, we get the same kind of result, but there's something wrong about that. Actually, if you start off your cookies in equilibrium in the classical sense, meaning there are no cookies, it's a Brownian motion. Okay, it's a random walk, but that's, in my view, a Brownian motion. Okay? If, on the other hand, we started off our cookie random walk with the cookie Markov chains all in equilibrium, it wouldn't go to a Brownian motion. Okay? What I would call the equilibrium is not actually product measure pi, the equilibrium for the cookies. That's not the right thing, actually. Okay? So now I'd like to just talk a little bit about, very quickly, I hope I do justice to it, the paper of Badevin and Singh, and how they worked out necessary and sufficient conditions for transience, and also necessary and sufficient conditions for ballasticity. So what they do is they look when you first hit n. Your Markov chain, your cookie random walk hits n. N, let's take n to be large, for the first time. N, positive n. Though, of course, you could look at the first time you hit minus n, no problem. But you're going to look at n. And now, of course, I've written if in capitals because, like the demented people on political blogs, I use capitals to emphasize things. Okay, this is, it may not happen. There's nothing that says your cookie random walk could be transient in the left, go to minus infinity. But what we can say is we can add, we have the realizations of the Markov chain, we can have IID sequences of uniform random variables, which based on the status of the Markov chain determine whether you go left and right. And we can work backwards from n using these Markov chain, using these random variables, and we can get a process, L of k, which L for the local time, but it's not the same as the local time, the classical local time being the number of visits. It's going to be the number of times you've gone from a site to the right. I could have gone to the left, but let's say it's to the right, okay? And the idea, I think, genius idea, going back to Ray and Knight, is just that if I know that from 10 along from the maximum, n, I have gone from 10 along to 9 along 20 times, then I know, actually, even though I'm saying I've gone from this site that's 10 along to 9 along, I know nothing about the Markov chain at the site 10 along. From this, if I sort of integrate over what's happening, I can say, well, I can say what's happened is, at this Markov chain, I look at the number of passes from 10 along to 11 along, 1 along, I look at that and I say, that number must be, for this Markov chain, the number of moves to the left from this Markov chain that I make before making LK moves to the right, okay? So from this, you can see, well, actually, there's a bias in that if there were no cookies, if I look at the number of moves to the left before I make 100 moves to the right, that's going to be, the expected number is going to be 100, okay? But on the other hand, if I have these drifts for the first m guys, that's going to, if the drift is hard to the right, that's going to push down the number of times I move to the left. The right is going to be favored. Secondly, there's a little bit of a subtlety here. There's this +1. Nothing hard or technical is going on. The +1 simply recognizes the fact that if you are k, I'm assuming k is between 0 and n, if k is a site between 0 and n, your cookie random walk started off at 0 and ended up at n. So for every site k, the flow is 1. If you're at k, you have gone from k to k plus 1 exactly one more time than you've gone from k to k minus 1. Okay? That's all. Okay? So what we have is the expected value of lk plus 1 given lk is this. At least if lk is larger than 1, so you've used up all the cookies, basically. Okay? And then you can say the variance, well, it's approximately 4lk, because it's approximately geometric, but of course, when you're starting off, it's not exactly, you don't get quite this variance. And it's a nice Markov chain. This lk is a nice Markov chain on 0 to infinity. I've just talked about the Markov chain here for lk large, but that's all you want. That's all you need to decide whether lk is positive recurrent or not. Okay? That's all you need. And the information I've given, A and B, all I've given, that I have given is enough to tell you whether you are recurrent or positive recurrent or not. If you're positive recurrent, that tells you X is transient. Why? If you're positive recurrent, by the time n is large, by the time you get back to 0, L is still a reasonable value. It's not a big, it's a nice, reasonable value. The probability it's less than 100, shall we say, is reasonable. It's not going to 0 as n goes to infinity. And that, if you think about it, is transience. If your cookie random walk was recurrent, you would be moving back and forth, coming to 0, well, infinitely many times. So you would have visited 0 infinitely many times before you hit something very large to the right. Okay? So you have that. And then you can say to yourself, what about ballasticity? Well, ballasticity, again, if for this stationary distribution, which is on the positive integers, if the value x is integrable, then that means if you look at the sum of the local times from 0 to n, it's going to be of order n, law of large numbers, which means ballasticity. If you have a stationary distribution, but it's not integrable, it's going to be bigger, of order bigger than n, which means the speed is 0, because the sum of the LKs is the time. Well, 2 times it is actually. Okay? So what we want to do is, and well, my co-workers, what they did was adapt this to the cookie walks. And for the cookie walks, what you do is you, this is Balint-Tot idea, but Balint-Tot really pushed this, is I have a Markov chain on 1 to the n. A priori, just its Markov chain. There are no jumps to the left, jumps to the right. It's just I'm looking at a Markov chain evolving. But I can say I have my function p, I can add auxiliary random variables, so I can add jumps. I can just sort of simply say, if at time 3 I'm at value k, with probability pk, I count that as a jump to the right. With probability 1 minus pk, I jump to the left. Fine. Okay. But what we're going to look at is the Markov chain value after the kth jump to the right. Or in other words, the Markov chain that's left once you've made k jumps to the right. This is what we need to look at. This is a Markov chain. It's nice, irreducible because of my assumptions on ellipticity. And this is going to have a stationary distribution. And of course, we can do exactly the same thing for a Markov chain, where we look at the jumps to the left. We look at where the cookie is after you've used up all the cookie, you've made your nth jump to the left. Okay? These are the things that enable us to work out something, to work out, to analyze transience and not. Because now, what we have is, in the same way, working our way backwards with exactly the same notation. If I tell you we've made LK jumps from n minus k to n minus k plus 1, and I also tell you that at site k, the initial cookie, I tell you it was I. I is a type of cookie. We started off with I. Then actually we have in the limit, so this is equals is a bit bogus. It converges. The right-hand side minus the left-hand side converges to 0 is what I should have said. We have, this is the expectation where the function r just depends upon I. This is a function, r plus. It depends upon I, and it's easy to see why this is, because you're looking at the difference between, when, under our circle, we'd expect when you've made n jumps to the right, you should make of order n jumps to the left, under our assumptions. But if you look at how many jumps you would expect to make from to the left between the millionth jump to the right and the millionth plus 1 jump to the right, you can say, well, this Markov chain is getting to equilibrium really, really quickly, so this expectation should be very exponentially close to 1. So you can say this limit, so that will tell you that the limit exists. Okay, we also can show that the variance of LK plus 1 given LK is approximately sigma squared LK. The first cookie doesn't matter in this, and that's not a surprise. And that's actually turns out to be, using the Bedevin-Singh argument, enough to tell you whether you can move off and explode to the right or not. Okay? Now, I'll just say a few words. You have these functions, R plus. I can do the same thing with R minus, looking to the right, going in the other direction. And we can say the integral of R plus with respect to the measure pi plus, which is the stationary measure for the process going to the right, this is going to be 0. Likewise, the integral of R minus with respect to pi minus. And this just corresponds to the integral of pi with respect of p with respect to pi being a half. So the difference being 0 between that being 0, because if this integral pi plus of R plus was, let's say, 3/4, then actually the number of you can sort of see that actually that would be, because our pi plus is always in equilibrium for the moves to the right. So you can see that actually that would imply you would be systematically making more jumps to the left than the right. Okay? And that can't happen. On the other hand, the integral of R minus with respect to pi plus, there's no reason why that should be 0. Though pi plus, integral of R minus with respect to pi plus is equal to the integral of R plus with respect to pi minus. But they're both not 0. And sigma squared just comes out. This is a calculation. I'm not so comfortable with these matrix algebra calculations, but it turns out that this has this formula. And the deltas that we spoke of, the deltas here, these determine whether it's positive, if both of these are less than or equal to 1, then your Markov chain your cookie random walk is recurrent. Okay? So again, the idea is your initial distribution of where the Markov chain determining the motion is, that's a bit like having a pile of cookies. Eventually, so that if it's stacked high enough, the initial effect is high enough, you will move off in one direction. Okay? Okay, now some more background knowledge that we use is square Bessel processes, and we'll see that the local times, as I've defined them, are very close to square Bessel processes. So this is just what a square Bessel process is. If D is integer, this is just Ito's formula for for the square of a d-dimensional Brownian motion. And what we can say now is, if you have just an ordinary Brownian motion, a single one-dimensional Brownian motion taking negative values, it's not a square. If you look at the time at which the local time for this Brownian motion at the site A is bigger than B, we have that the local times at this point satisfy the following. To the right of A, the local times behave like a Bessel squared process began at B. In between 0 and A, the local times are like a Bessel squared 2. It's not immediately clear why that should be, but that's how it is. And then beyond 0, we're back to it evolving like a Bessel squared 0 process. Okay? And this is particularly of interest to us. This works if you take B to be 0. If you take B to be 0, the first what you're really talking about is not the first time the local time at A exceeded B. You're talking about the first time the Brownian motion hit. The first time the Brownian motion hit A. Okay? So what this says is if you start off at the origin and you look at the first time you hit A, the local time as you work your way back from A back to 0, space 0, but it's also time as an index of the local time process, that's a Bessel 2 process. So it never, ever actually, it starts off at 0, but apart from that, it won't hit 0. And then it hits 0, and at that point, beyond that, it evolves as a Bessel squared 0 process. Okay? So for us, all we're doing is simply saying, if you look at a Bessel squared 2 process, you run it for time 1, and then you look at a Bessel squared 0 process, starting off at this random point at time 1, and you run it. You can ask yourself, what is the chance that process hits 0 before time 2? Okay? A priori, that's quite a complicated question, but actually, it's just a half. Because your process hits 0, that means that corresponds to the fact that when you hit 1 for the first time, you have not hit -1. If the local time, working your way back from 1, if the local time had not hit 0 by time 2, that's the same thing as saying -1 has been hit. Okay? So that's going to be very useful for us. Okay. And again, these kind of results were generalized by Carmona, Petit, and Yor for Brownian motions perturbed at extrema, which are very, it's the same kind of results for the same reasons, though that doesn't make it the extension technically insignificant. And notice again, if you have, for this result, I don't think you need to digest it. We won't really be using it in the talk, but we do use it in our paper. But notice that if alpha or beta is 0, then you get Bessel squared 0s and Bessel squared 2s, as you should. Okay? So now, again, I want to look at the diffusion approximation now. Diffusion approximation, as you move from, let's suppose you look at, I'm going to look at things for our cookie random walk. As you move, I'm going to scale things diffusively. You look as you move from x square root of n to x square root of n plus 1, sorry for the typo, for the gamma square root of nth time. What we have here, if you do this calculation, is you have these laws. You have these laws for what I'm calling the local times. Okay, we know the local time at x, when you renormalize it, meaning divide by square root of n, the local time is going to be x, it starts there. It's going to be y, excuse me. But apart from that, what we're going to see, I don't want to dwell too much on this, but what we're going to see are, these are going to behave like the following processes when you renormalize them. They're going to behave like multiples of square Bessel processes. Okay? So we have these square Bessel processes, and the point about that is if you look at any particular time, like this, the local times, wherever you go, as long as you're in the range, the local times are going to be very, very big. What does that mean? That means, if you're looking at the first time you went from x square root of n to x square root of n plus 1, to the right, what you're looking at is a Markov chain. If you're looking at a site to the right, you're looking at a Markov chain which has moved to the left. It's moved to the left because you're at x. Now at the time you're at x, so the cookie Markov chain at site y, which is to the right of y, it's made a lot of moves to its left, and where it is the site, is the position after, shall we say, 1,000,000 moves to the left. So it will be very much in distribution pi minus. Equally, the distribution to the left of x, will be very much in distribution, the cookies will be like pi plus. So what you have is, you have essentially product measure, pi plus to the left of where you are, up until you, of course, on the range, then you, of course, you get to the initial distribution, and you have pi minus to the right, up until you get to the maximum, okay? And these are essentially almost product, but it's a bit difficult to say they're exactly product, but they are almost product. And what we can do is actually we can argue that essentially we have in this law of large numbers sense that our processes, from this crude averaging sense, we have that the distribution of the Markov chains is essentially product measure pi plus to the left, pi minus to the right. And in fact, this is what I claim should be the real equilibrium. If you looked at our cookie random walk, but you looked at it from where the cookie actually is, an equilibrium distribution would be product measure pi plus to the right, to the left, excuse me, pi minus to the right, and pi, the equilibrium of the Markov chain, at where you are. And so from that, you could actually work out, you could show Brownian motion by the usual Kipnis-Varadhan kind of methods, I think. I haven't gone into that, but I've talked to cleverer people who understand these things, and they think it is, but they haven't staked their reputation on it. But the point is, that's not going to work for us, because first of all, we're looking at things which are not in equilibrium. They didn't start in equilibrium. Secondly, we're looking at things that get perturbed when you get to the maximum and the minimum. Our limit isn't a Brownian motion. So we need something a bit different, but so what we have, though, is our strategy is now to look at things. It's just a coarse graining strategy. We look at, for our walker, we look at when you have moved a distance epsilon square root of n, to the left or the right. That's the first stopping time. Then you look at the next time you've moved epsilon square root of n to the left, epsilon square root of n to the right. This is a very natural thing to do. Eventually, what we're going to do is we're going to fix epsilon, let n go to infinity, and then we're going to let epsilon go to 0. This is a very natural thing to do, okay? And the point is, I'm just going to look at this, actually, when we're in the bulk. There's something else to do. By the bulk, I mean your walker is more than epsilon square root of n away from the maximum or the minimum, okay? So in this case, if I'm, as I call it, in the bulk, I can do this. I can look at the local times, meaning the number of jumps you've made. I can look at the process running, starting from xtkn, the kth stopping time. And I look at the number of jumps you've made from a site to the right. What I have, for the reasons explained, is that, oh, there should be a Brownian motion there. What we have, though, is these local times. If I look at the first time I went epsilon square root of n to the left, and I work my way back along the local times, what we have, just from our averaging, is we have enough, more or less, to say that the local times, as you move, starting off at a shift of epsilon square root of n to the left, and you move over and you go rightwards, the local time is going to behave like a Bessel squared 2 process, with a and then it's going to be, it's going to behave like a Bessel squared process like that. And then after that, once you cross your initial site, the local time is going to behave like a multiple of a Bessel squared 0 process. So, because, I'll just flip back, if you look at these values, the drift is 1 plus pi plus r minus, and the multiple there, the sigma, well, it's just some number. But the fact that sigma squared divided by this is multiplied by 4, as it happens, is actually equal to 2, is why this process is going to be a Bessel squared 2 process, or a multiple of it. So what that tells us, very, very simply, is that just because of this basic averaging property of the cookie environment, the chance, if you're in the bulk, of moving to the left or the right is pretty much a half. And this pretty much a half, as n goes to infinity, actually will, in the limit as n goes to infinity, will be exactly a half. Okay, you've got to sort of do a similar kind of thing for when you're at the extremities to get the right probabilities. And you've got to take account of where the maximum and the minimum are. But you can do the same kind of thing. One thing that I've swept a little bit under the carpet is the fact that the conditions I've got for the equilibrium, for the Markov chain environment being essentially pi plus, pi minus to the left, pi minus to the right, those conditions there, they're very good for getting the diffusion approximation to a Bessel process up until you hit 0, okay? Unfortunately, we need to work a little bit harder, and we have to do some little technical trick stuff to get what we want, because the convergence of the diffusions, a priori, it could be your process starts off, your local time process starts off, and then it gets down to 0. But actually, the real cookie local time process, it looks like it's at 0, but actually it's never quite at 0. It's just at something small compared to the square root of n. And that would sort of ruin everything. So we have to find a way, which we did, of showing that the diffusion approximation gives you the actual probabilities. Once you've actually got that these probabilities are the correct probabilities, the probabilities of moving are the correct probabilities, they correspond to Brownian motion perturbed at extrema, it's game over, because now, as I say, you just let n go to infinity, you let epsilon go down to 0, and you get your Brownian motion perturbed at extrema. Okay, so I'll stop there.
Any questions?
Oh.
Do you have any hope of doing something like ZD?
Oh. Do I have any hope of getting anything on ZD? No. Ask Pierre. Pierre Therese might know. I'm not so ambitious. No, maybe I should be, but no. I mean, this whole approach relies very much on the Ray-Knight approach of Badavin and Singh, and without that, we would have nothing. Tree, yes. Absolutely, sure. Yeah, tree I'd be happy with, yeah. I mean, and Badavin and Singh also have done work on tree, with trees. I mean, got interesting paper there, yes. In high, oh. Yes. It gets very, I'm sorry? A limiting object for, the question asked is there a limiting object? And you mean a limiting object for the, for the site's visit, for the range? An invariance principle for the, yes, yeah, I would imagine yes, and I don't really perturbed at extrema, but we could, yeah, I think it would be a natural analog of these Brownian motion perturbed at extrema, yes. But I don't think that's been studied actually. I think because I think the perturbations are going to depend upon angles and things like this, but I don't think that's been studied, but I think I would say, A, yes, there is. There are analogous objects, and they would correspond to a renormalization of this process, of the Markov cookie random walk in high dimensions, yes. I must confess, I've never thought of that. Jason?